So in this session on signals and systems, we are going to give an introduction to impulse function and convolution integral. So let us start. Let us first of all define the unit impulse function. So first thing we note is that symbolically the unit impulse function is represented by delta t, and one of its properties is that delta t is equal to 0 for all values of time which are non-zero. Okay, that is the first property of the unit impulse function. But what happens at t equal to 0? Now this is a very remarkable signal, and what happens at t equal to 0 is something unique. From 0 value it jumps to infinite value and comes back to 0 in 0 time. In other words, you cannot really define the value of delta t at t equal to 0. Nevertheless, we can say that it jumps to infinity in 0 time. That is what it does. In that case, what do we mean when we call this impulse function as a unit impulse? Unit is associated with what? Now, in order to understand that, let us first of all try to see how the unit impulse can be generated by using a limiting process. So let us look at this diagram where I have shown a number of rectangular pulses. Let us look at the first one here, the blue one. And here if you look at its base width, it is from -5 to +5. So the base width is 10 units and the height, as you can see, is 0.1. So if you calculate the area, 10 multiplied by 0.1, that is equal to 1 unity. Now suppose we halve the base width. In that case, what we do is we double the height of the pulse also, so that the area remains same. If we further reduce the pulse width, we have to increase the height further. In the limit, as you can see, that if the pulse width approaches 0, the height will approach infinity and this rectangular pulse will approach an impulse. However, the area under that remains constant at 1, and that is what we mean by unity. So unity refers to the strength of the impulse function, and it is defined as the area under the impulse function. So if you integrate from -infinity to +infinity delta t with respect to time, you will get 1. That is the meaning of the unit impulse function. Understand that this is a theoretical model and it cannot be realized exactly in practice. The only thing you can do is to generate a very narrow pulse of a very great height. That is the only thing you can do to approximate an impulse, but you cannot exactly use this. However, it's a very important function because, as we shall see, a lot of analysis can be done by the use of unit impulse function for signals as well as systems. All right. So whatever I have been saying here about the generation of the unit impulse by using the limiting process is repeated here. As the pulse width reduces, we increase the height to keep the area equal to 1. As the pulse width approaches 0, the pulse becomes an impulse. All right. Next, note one important and simple property of this unit impulse function. Note that for all values less than 0, for all values of time less than 0, delta t is 0, and for all values of time greater than 0, again it is 0. So we can say that impulse function is an even function of time. So delta t is equal to delta of -t. All right. So that is the definition and the explanation about the unit impulse function. Let us now study a few properties of the unit impulse. First of all, we study the property called as a product property. Here we are multiplying the unit impulse by some generalized function xt. Xt can be any function of t, and we are taking the product of xt with delta t. Then what do we get? We still get a impulse function, but the difference is that its weight is now different. So xt multiplied by delta t will be equal to x0. What is this x0? This is actually xt evaluated at t equal to 0. So x0 multiplied by delta t. This means that although the product also gives you an impulse function, its strength is no longer unit, it's equal to x0. Now, why does this happen? You can imagine that for all values of t which are non-zero, delta t is going to be 0. So no matter what is the value of xt, it will not play any role as far as the product is concerned. So only that value of xt will play a role which is at t equal to 0, because around 0 delta t has some meaning. So therefore, since this is the only value of significance, output is x0 multiplied by delta t. Alright. Next, suppose you delay the unit impulse by say alpha seconds. Okay, then it will look like this. Previously it was existing at this point, but now it is 0 going infinity at t equal to alpha. In fact, the impulse simply shifts to the right, as we have studied before. Whenever you delay a function, it shifts to the right by a definite amount. In this case, we are assuming that it shifts to the right by alpha seconds. In that case, just as we have discussed this, if we take the product of xt and delta t minus alpha, you can imagine that you will still get an impulse function, but now its strength is x alpha and no longer unity. Alright, so that is the product property. Now another property which is important is called as a sampling property. So suppose you take this product and integrate from minus infinity to plus infinity. Then again, as we have discussed before, the only value of xt which is of any significance is the one that is evaluated at t equal to 0. So x0, we take it outside the integral sign, and minus infinity to plus infinity delta t dt, we have already seen that this is the area under the unit impulse, and that is equal to unity. So x0 multiplied by 1, you will get x0. Alright. Similarly, you can imagine that if you multiply xt by the shifted unit impulse and integrate, then what you will extract will be the value of xt at t equal to alpha. So since we are extracting the value of xt at a specified time, this property is called as the sampling property. That is, you multiply the given signal by a shifted unit impulse and you sample the value of the xt itself at t equal to alpha, where alpha is the delay time. Okay, so if alpha is 0, then of course you get x0, but for other values of alpha you get x alpha. So that is called as the sampling property. Alright. Now as we shall see, the impulse function is important because we are going to see that if the impulse response of any system is known, we'll see what an impulse response is in a moment. I'm just trying to tell you the importance of the impulse function. If the impulse response of the system is known, then the output can be evaluated for any general given input signal. That's the importance of the impulse function. Alright, anyway, let us continue to study these properties. This we have already studied. Now suppose we change t to tau. This is a mathematical manipulation, and you will see the reason for doing this in a short while. So suppose we change t to tau and alpha to t, then what will you get? So this t becomes tau, okay, this t becomes tau, alpha becomes t, dt becomes d tau, and this x alpha becomes xt. Now since the unit impulse is an even function of time, even if I write this as minus in the bracket tau minus t, tau plus t, I will still get the same result. So I can simply invert this and I'll still get this. So this is minus infinity to plus infinity, x tau delta t minus tau d tau equal to xt. So we have essentially expressed xt in terms of the shifted unit step functions and the value of the xt at a given time tau. That is what we have done. And then we have integrated the product and obtained the xt. Understand this. Here integration is with respect to tau. So after integrating with respect to tau and you put the limits, what will be left will be a function of time. So you will get xt here. All right. Having studied this, see, ultimately what we are trying to do is to show that the output for any input can be calculated by knowing the impulse response of the system. That is what we are driving to. So these are all in between steps for reaching that goal. All right. So in order to be able to achieve our goal, we first define what is impulse response. So suppose you have some system, and this system we are assuming is linear time invariant system. Now in our sessions of lectures, we have not really studied system properties, that is linearity, time invariance and so on. And at some time we'll study that, but understand these are all supplementary lectures. So the detailed derivations are often done in the theory class that you study. But here my aim is to provide you some quick introduction to the subject and also a little bit of programming. When you do the programming, then you will understand how digital signal processing is actually done. Anyway, so we are assuming this system to be linear and time invariant, and this linear time invariance property we are going to apply in the derivation that follow, and I'll explain that in a moment, that property. You might have studied it in the theory class. Okay. So let's say system is a linear time invariant system. So it can be described by a differential equation. So if delta t is the input to the system, by the theory of differential equations, you can solve the differential equation and the solution will be the output. So ht is the symbol that is used typically in most of the signals systems books to denote that this is the output when the input is a unit impulse. So this is called as the impulse response because it is the output when the input is a unit impulse. All right. So whatever I have been saying is summarized here. We assume a linear time invariant system. If the system components are known, its differential equation can be found. And this can be solved for the impulse input. We denote the output as ht, called as the impulse response. Okay. Now let us study the input-output relationship by using the relationships that we have studied so far. So suppose xt is my input, and for a given system, let us say that corresponding to xt, yt is my output. Now if input is delta t, we have already said that we designate the output as ht. Now since we are assuming a time invariant system, if I delay the input by tau seconds, the output also gets delayed by tau seconds. So if the input is delta t minus tau, then the output is ht minus tau. Okay. Then we use the linearity property of the system. So if the input is multiplied by x tau, the output also gets multiplied by x tau. So if the input is x tau delta t minus tau, then the corresponding output is x tau into h of t minus tau. And finally, linearity property also tells us if you integrate the input, the output also gets integrated. So if we integrate this, we get this expression which we have already seen is equal to xt. And if you integrate this expression for the output, this is what you get. So you can see here that the output is expressed in terms of the impulse response, no doubt delayed by tau seconds, and in terms of the input. So for any input, if you can evaluate this integral, you can calculate yt, provided you know what is the impulse response. That is why this integral is a very important integral, and it is called as a convolution integral. So yt equal to minus infinity to plus infinity x tau h t minus tau d tau This is called as a convolution integral and is in short denoted as yt is equal to xt star ht. Normally in programming languages we use star as multiplication, but in theoretical discussions we use star here to denote that it's a convolution between xt and ht. So what is a typical problem in convolution studies? Typically impulse response is known, xt is given to you, xt is given to you, ht is given to you, and you want to find out yt. So you have to perform the convolution. So what are the steps in evaluating the convolution integral? That is what we want to study. So as I said, xt and ht are given and we have to calculate yt. So what do we do? So first obtain x tau from xt by replacing t by tau, because we want this. All we have to do is to xt as a function of time is given to us, so we simply replace t by tau and plot this. Okay. Then obtain h tau from ht by replacing t by tau. Same thing we do for this. Then invert h tau to get h of minus tau. We want this. So now you'll have to delay by t seconds, that we have already studied. So delay by t to get h t minus tau. Then multiply h t minus tau by x tau. Okay, x tau multiplied by this, and finally integrate. Only thing, when you are doing this integration, keep in mind that ultimately you are going to get a result which is a function of t. So when you integrate this product, you have to be careful whether the product has same expression over all times. If it has same expression over all times, some of the problems may be simple, and when you take this product, the expression of the product may be same for all values of time. In that case, you can directly integrate that and get your result. Otherwise, you will have to. So as I said, when the expression is same for all t, has to be just once. Otherwise, for certain ranges of time t, various product expressions and limits have to be found and integrated. So this will become clear when we perform a number of examples for analytic solutions to the computation of convolution integral. When we do that, this will become clear. See, basically what we are doing is, we got h tau, we inverted, then for various values of time, so your delay you keep on changing. So you are essentially sliding this function past this function and evaluating the integral of the product. That is what we are doing. So this sounds complicated, but when we solve examples, it will become clearer. All right. Now, one important property of the impulse convolution integral is that it is commutative in nature. So again, I am just stating it can be proved, but right now I am just stating it, and we are going to use this result. So if you write the expression in this form, you write it as xt star ht. But if you instead of x tau, you use h tau first and then delay x, then it is written as ht convoluted xt. But commutative property tells us that the order of operation doesn't matter. Whether you take xt first or ht first, the result is going to be same. That is the commutative property of the convolution integral. So to find the output for any input xt is convolved with the impulse response. So whether you do this or you do this depends on whichever is easier to calculate. And that's all as far as this session is concerned.